Thanks for the introduction. Thanks for inviting me. And thanks, Libor. I mean, he took more time than he should, but I think he saved also some time because he perfectly introduced everything I need to say, basically, about the topic of my talk. Yeah, basically, I will speak about the anomalous Hall effect in such an ultramagnetic thin film material. The work was actually mostly done by one of our master students, Ruben, Honza in Prague. On the theoretical side, more by Raphael and Libor and Jakub, actually, yeah, spread over all the world. I think these are the slides I will go very quickly because basically Libor had full talk on my introduction. Basically, this classification of magnets, as we just have learned, should be revisited and extended. Basically, in school, we learned for the collinear systems maybe already that there are two classes. However, there should be actually a third one. The distinction is actually that for the systems with the compensated systems, where we typically would have no net magnetization, no spin splitting, because there is no breaking of time reversal symmetry, as long as you have these opposite sublattices related by inversion or translation symmetries. And yeah, as we just have heard, there is this additional class of magnetically ordered materials where these different sublattices are not related by translation or inversion, but instead by rotation. This is the picture for the famous ruthenium dioxide, which we will hear about more. But I will speak about something where also there is a rotational connection between the two sublattices. We will see in a few slides. This has consequences, as we have seen, which results in some alternating spin splitting in the momentum space, which can be also very sizable. And this alternating spin splitting also led to the suggestion of the name of ultramagnets. So here the full table of these magnetically ordered systems. And although we have here a collinear magnetically compensated system, we might have a breaking of time reversal symmetry in the electronic band structure. So we have spin splitting allowed. And also related effects could suddenly be possible in these systems, in these compensated systems, which were previously thought not to exist, like anomalous Hall effect. And that's actually what I would like to talk about today, anomalous Hall effect in the ultramagnet manganese telluride. Manganese telluride is a material which is also studied already more than 60 years, likely. So here are some the picture from a paper from the 60s where they already had neutron diffraction data and confirmed this antiferromagnetic order. It's a hexagonally ordered material where you have planes of manganese which have ferromagnetic planes of manganese which are stacked then with an antiparallel magnetic order. So here the more modern version of the same picture with some errors for the magnetic moments. And as you can see, or it should be we try to illustrate here, the different manganese sublattices, they are actually not linked by translation because translation symmetries are prohibited by the existence of these tellurium atoms which occupy non-central magnetic positions. And instead, the two sublattices are linked by a rotation/screw axis along this hexagonal C direction. And this actually makes this realization of this class of ultramagnets. Therefore, as we have heard, there should be spin polarized bands allowed, or we should be able to find them in the band structure. And in fact, we do, but you have to look a bit more carefully because for the typical observed directions in these spaghetti plots, you actually find only degenerate directions, but you have to really go into a specific direction. In this case, it's between gamma and L point, so between the center of Brillouin zone and one of these edges, the top here, and there you can also find sizable splitting in the electronic bands. And therefore related, you can also obtain, all by first principle calculations done by mostly by Raphael, you can find anomalous Hall conductivity, which can be also several hundred Siemens per centimeter when you go far enough away from the valence band edge. So this is as you can see here, we have a band gap. So this is a semiconducting material, which also will allow most likely to combine now these sort of spin transport properties in a magnetically ordered system with semiconducting properties. Experimentally, we were able to grow these films. This is done by colleagues in Linz in Austria, where they can grow quite high quality thin films with C-plane orientation, so this means we have the hexagonal plane in our sample plane, which is exactly what we actually need to study the anomalous Hall effect, which, yeah, this is the right plane, so to say. We come more to that later. Yeah, here also the band gap we experimentally found to be roughly 1.4 electron volts. Yeah, so we process these thin films to Hall bar structures and by basic lithography, and we study the longitudinal and transversal resistance but when we perform field sweeps in this sort of tilted field geometry. So the field is between the in-plane current directions and the out-of-plane perpendicular directions. We do this at different angles here named beta. And when we do that, first maybe let's talk about the longitudinal resistivity. Here we see plane AMR. So while we start to apply this field, the Néel vector can sort of reorient, and therefore we can see anisotropic magnetic resistance. The transversal data is what we are interested in when we look for the anomalous Hall effect. They're actually dominated because we have an out-of-plane field component. This is dominated by the ordinary Hall effect. However, when you look in the center, there's already, you see there's some sort of opening. So we process this data a bit. So we remove the linear slope from the ordinary Hall effect, and also there's of course an AMR contribution to transversal contact, which we also removed. So I show you only the antisymmetric remaining signal, which is then seen here, but already in the raw data, if you look carefully, you can see the loop of the anomalous Hall effect. Yeah, and this is basically how we found that what governs our Hall effect is the out-of-plane field component. As you can see, when we do this measurement with the field sort of at plus 30 degree or minus 30 degree, we get exactly the opposite sign of the signal. And in addition to maybe, and also in big distinction to the case of ruthenium dioxide, which Livo has flashed before, we actually now get also really a spontaneous signal at zero field. So when we remove the field, we remain with some different transversal resistivity. And how we understand this is actually, I try to illustrate here. This might not be the final picture, but we try to imagine it like this, that when you actually apply a magnetic field, you might actually count the moment a bit, and by this counting, which couples then also to the in-plane magnetic order, you are able actually to reorient not only also, when you apply a positive or negative field, what you do is you also at the same time reorient the in-plane Néel vector. So this means that you see here, here the moments count upwards, and this moment points to the left. When you do it negative, it's actually counting downwards, but it's at the same time forced to point to the right. And therefore, then two nearly magnetic compensated states remain when we remove the field, which have opposite Néel vector. So just the polarity of the Néel vector is different, and this gives us the different sign of the anomalous Hall signal which we observe in the experiment. I should note that the tilting here is certainly very much exaggerated because in the experiments we can actually not measure this magnetization. So we did a few sanity checks to check that this signal is really related to our manganese telluride. So we know from neutron diffractions on the thin films and from susceptibility measurements where the transition temperature is, which is actually like in the bulk around 300 Kelvin, and the observed anomalous Hall conductivity actually also vanishes when we approach this 300 degrees, as it has to when it is related to this magnetic order in the manganese telluride. So how this actually depends on the in-plane orientation of the Néel vector is also somehow interesting, and we studied it theoretically as well as experimentally. And therefore, it's important actually to understand that, as Livo has told us, basically we can have this spin polarization in the bands just because we have the different sublattices related by rotational symmetries without any further requirements. So we don't, in this case, actually it would not matter in which direction these two opposite spin sublattices point. However, for the anomalous Hall effect, it's important that at the same time we also have to it has to be allowed a pseudo vector which corresponds to this anomalous Hall conductivity, and this actually can be very sensitively dependent on the direction of the magnetic order. And here I showed 2 times the same structure with different magnetic order orientation. Just you see that once we point along the A direction and 130 degree away from that, and the magnetic symmetries are in details are different because of that. And only in the left case, this anomalous Hall pseudo vector is able to exist along the plane perpendicular to the slide. And in the other case, this actually has to vanish. Yeah? This is because of this existence of this mirror plane in analogy to what Libor has shown us. You can also imagine it when you want to think about it in 3 dimensions with the rotation axis, but this would maybe go too far to look into that. But basically, because we have 3 orthogonal 2-fold rotation axes here, you cannot have any pseudo vector existing because it would always be transformed by one of these symmetry operations into a different state, and therefore it has to vanish. So this means when we now perform a calculation where we rotate the magnetic order in this basal hexagonal basal plane, then we see that the component of the conductivity tensor, which corresponds to the transport in this basal plane, is actually showing this anomalous Hall effect, vanishing and appearing with a 6-fold or 3-fold symmetry, I should say. Yeah. So we have it every 60 degrees, we have it positive or negative. Every 60 degrees, we have it vanishing. Yeah. And we also tried to look at this experimentally. So theory predicts basically that we should have this 3-fold term in the transversal conductivity or resistivity, which should correspond to this anomalous Hall effect. When we do this experimentally, we get this rather complicated or complex traces because in addition to this anomalous Hall term, there is allowed also some AMR terms, and in the longitudinal case, this can be actually, there will be even higher ones, but in theory they can say that at least the 2-fold, 4-fold, and 6-fold are allowed to exist, and these are actually the main ones we observe here in the experiment. In the transversal case, this is the data we have, and we studied the amplitude of the different harmonics in terms of powers of the angle of the Néel vector here, or in the experiment in powers of the magnetic field angle, I should say. And we see, yes, indeed, the main components are the 2 and the 4 as they are sort of predicted by theory. The 3-fold one, in fact, is also here, but it's rather weak. And this is consistent with what I have shown you before, that we actually need an out-of-plane field to polarize the system. With the pure in-plane field in the experiment, I'm afraid we are not able to distinguish the 2 different polarities of the in-plane Néel vector, and therefore we have no really defined 3-fold signal in this in-plane experiment. Nevertheless, it helps us to understand why we can have a spontaneous response in the magnetotransport, because we understand from this variation of the signal. I show here in detail one of the curves of the longitudinal resistivity, where we see clearly that the minima are always wider than the maxima. Yeah? And from that we can conclude that basically for this field orientation, our system is in its easy axis orientation. And from that, we know that the easy axis orientation indeed corresponds to the one scenario where the anomalous Hall effect is allowed. And this is sort of distinguishing this material from the ruthenium dioxide, I would say, where you actually need the field to allow the anomalous Hall response. Here we can have the anomalous Hall response also in absence of a magnetic field, which explains the observed spontaneous Hall signal. Yeah, with this I would like to summarize. So basically we studied these manganese telluride thin films. I hope we convinced you that we have a magnetic order which is consistent with this ultramagnetic picture, and therefore we also could observe a spontaneous anomalous Hall effect and some, let's say, rich angular dependence in the magnetic resistance.